Yeah, hi everyone, and this is Saurabh. Two back-to-back machine learning talks on a Wednesday afternoon is perhaps not what we would have expected, but so I'm going to call it statistical methods from now on. And as the title suggests, my research right now, which I'm presenting, is more of a recommendation for future in situ missions. And what I find is applicable to remote sensing applications as well. So let me just give a brief idea of what I'm talking about. So in future missions in which payloads will be carried by rovers, which are capable of performing geochemical analysis, if we want to identify what are the different rock types using just the geochemistry, that's where we want to use the methods that I'm going to recommend in this talk. To summarize the two goals that I'm interested in, if we want to send a rover to the moon with instruments that are capable of performing geochemical analysis, such as, let's say, LIBS, the first task is to classify different lithologies, which are based on geochemistry. They are distinct from each other. So we don't necessarily need to identify what the rock type is in this first goal, but we want to see if rock A and rock B are different in terms of their geochemistry. And the second goal is to see if we can actually identify what rock type it is, using, again, the bulk geochemical data in this case. So for that, before I go into the methods, typically what we do to identify any lunar rock is, first of all, rely on the visual information in the first place. So if we have a rock which is, let's say, dark in color, we can say that it is a Mare basalt, for example. And if it is in light tone, it might be a highland rock. In this example, it is a Mare basalt and an anorthositic clast, I guess, which we are seeing there. Similarly, we also rely on other visual parameters such as the texture of the rock, which gives us other insight as well. But to be absolutely sure, we rely on the samples that are returned back, and we do, let's say, the mineralogy and the geochemical makeup in the mineral that we identify in the rock. So that is what we do to typically identify what a rock type is. But if we are sending a rover and all we are getting is the data set in geochemical format. So let's say if we have identified several rocks and we have the geochemical data for them, what do we do to classify them into different lithologies? One of the main questions that is driving this thing is this research is that if I'm identifying, let's say, N rocks in the traverse path of a rover, if the nth rock sample is similar or different from the other N-1 rocks that have been identified, that is one of the criteria which could be interesting in identifying if the new rock sample is interesting for peering into a new insight in terms of geochemistry, for example. And the idea here is that if I combine the geochemical data into, let's say, 2 dimensions, then we can project them in a 2D space. And that would be easy to visualize the different clusters that are getting formed. And the nth rock sample that I'm talking about here, if that plots within a certain cluster, which we are identifying in this 2D space, then that might give us a suggestion that, hey, perhaps this rock type belongs to those other 4 rocks that we are identifying in that cluster. So that's what I'm trying to do here. And as a combination method of all the geochemical elements that I'm taking here, I'm considering a linear combination method and a non-linear combination for comparison. So the linear combination method that I'm using here is the principal component analysis, which is a fairly well-recognized algorithm in any data science community. And the idea is that if we are using the data set, which has, let's say, these n dimensions, which would be the geochemical data, the idea would be to combine them in a linear format as a coefficient A1 into SiO2 plus B1 into TiO2, and yada, yada. In the comparison space that you see as the right side, or the left side in your case, image, which is the TSNE, it stands for T-distributed stochastic neighborhood embedding, and for the sake of time, I'm not going to call it that. So let's call it TSNE. And in the TSNE space, we combine the same geochemical data in a non-linear manner. And using the probabilistic distribution, for example, we get another insight into how the data can be arranged. And the idea was to compare if the linear combination or the non-linear combination could be used for such purposes. So to do so, if we have to identify what clusters these are, either we can look and visually look into the data and try to identify the clusters, And before I go further, I just wanted to highlight that right now I'm using the geochemical data from the Apollo samples as an example for what we could be doing in future lunar missions. So what I do then as a next step is, instead of me recognizing what the rock types are, I could rely on a cluster recognition method in which the computer technically recognizes what these clusters are. And a combination of, let's say, PCA plus k-means or TISNI plus k-means or some other cluster recognition methods, which can be driven by other mathematical logics, could determine what these clusters are. We could also have different optimizing parameters to identify how many clusters we could identify. That could give us perhaps an idea of how many clusters there are in this 2D space. And to check if this is actually doing the task that we intend it to do, I classified the labels that are actually associated with the rocks that I'm using here for the 2D space. So if we try to just jump between back and forth, you might be able to catch that some of these clusters are overlapping with each other, but some of them are not. So the idea was to classify the clusters into different spaces so that rocks, which are typically recognized within a single label, such as, let's say, the anorthositic rocks, are clustered together. And as you might be able to see that within the anorthosites as well, there are the alkali anorthosites and the ferroan anorthosites, which are getting clustered differently, but within the same space as compared to the other clusters. So this is direction to suggest that we might be able to classify, let's say, the anorthosites from the other magnesium sweet rocks, for example. And within the anorthosites, we might be able to peer into much deeper insights, whether these are ferroan anorthosites or other types of anorthosites, for example. So that's where the clusters are recognized. And as we can see that the PCA method has a lot of overlap between different points, but the TISNI space could suggest that we have some separation between the different clusters that can be labeled here. But if I have to suggest that, let's say we are sending the rover to a location of the moon from where this data set is not necessarily applicable, because all the Apollo samples were returned from the near side of the moon. If we are going to a location which is compositionally, which might be different, is this method actually applicable in terms of recognizing the rock type or not? For that, I put some meteoritic data just to see if they can be plotted together along with the clusters that we identified here. And all I can see here is that within the anorthositic space, the plus signs that are marked there, if you might be able to look into that, these are all the meteoritic data and that were recognized as anorthosites that map within the anorthositic space. And as you might be able to see that most of the anorthositic meteorites cluster along with the anorthositic cluster, and the basaltic meteorites and the gabbro meteorites cluster along with the noritic within the noritic space, which is again mafic in composition. So it provides promise in terms of recognizing the rock types as well, even if we are going to a different location. Another interesting idea that we get out of this study is that even without, let's say, the information of what the SiO2 content is, let's say if we are not able to measure SiO2, could we still classify, let's say, the felsic rocks? And the felsic samples that I've used here, they are getting clustered together separately from the other rock types, which also provides a promise that we might be able to recognize using the combination of other geochemical data to identify the felsic lithologies as well. So in conclusion, if the goal is to classify geochemically distinct lithologies, which was the first goal of this research, my suggestion would be that we could use a non-linear combination of data, and such as the method that I used here is the TSNE, or there are other methods as well, such as UMAP. These methods have a lot of parameters and hyperparameters in machine learning terms, which we can optimize to get better clustering. And when they are combined along with the cluster recognition methods, such as k-means or dbScan, we can identify the clusters as well. One of the issues with that is that if we add new data points, the same space that was created in the previous iteration of the TISNI plotting is not reproduced in the next iteration. But if we want to identify what lithologies do we identify within the space, again, the promise the non-linear combination showed promise in terms of recognizing the lithologies without too much overlap. So that's one of the other methods that could be used and could be trained along with the existing database of the geochemical data that were returned from the Apollo samples. I'm sorry. And there are other methods, even if we are using the linear combination methods, if we want to identify the lithologies, and we already know the labels associated with some of these existing data sets, then supervised machine learning techniques, such as a dimensionality reduction method called LDA, could be used and for applications to the second goal of this research. With that, I would like to say thank you.